Touch input has become the dominant means of interacting with today's mobile devices, and has made inroads into desktop computing as well. While the performance of commercial touch devices has improved in recent years, many popular devices exhibit a high level of latency between a user's touch and the on-screen response. This lag is often 100 milliseconds or more. In contrast, studies have found that users can perceive as little as 24 milliseconds of touchdown latency. While completely eliminating latency may ultimately prove impossible, we believe that it is possible to reduce the perceived latency of an interactive system. In this video, we introduce a novel technique for removing perceived latency from a touch device. We model finger movement and predict landing points by sensing the position of the user's finger above the touch surface. Our prototype uses a high-fidelity 3D tracking system to feed the model 60 frames per second of tracking data from a single point, a technique that is generalizable to other sensing methods, such as capacitive hover sensing. Here, the user reaches out to touch a target on a tabletop surface. Without the aid of our prediction model, there is 150 millisecond latency between the user's touch and the corresponding visual response to that touch. In this case, the response is the circle changing from green to white. Here, the user reaches out to tap again, this time with a tracking device attached to their index finger. We track the path of the finger as it approaches the touch screen and map it onto our predictive model to determine a landing point location and time. We forward this information to the application before the finger lands on the screen. This is timed so that the response is shown to the user the instant they touch the display, eliminating the perceived latency. To develop the model, we collected data from 15 participants, asking them to execute a series of tapping tasks. From a total of 2,880 trials, we identified two important phases of the touch trajectory: lift-off and drop-down. We use the start and end points of these phases as heuristics to time the release of prediction info to a touch application as we become more confident in them. Here, we trace out the arc of a tapping action at 1/8 speed. The liftoff phase begins with a user lifting a finger off the touch surface and ends when the finger reaches the apex of its arc. Despite being non-planar, the direction of the finger from start to end of this phase is very close to the direction of the full trajectory. Thus, at the end of this phase, we give a prediction of the direction of the future touch. We enter the drop-down phase when the tangent of the arc passes 23 degrees below the horizontal. This part of the trajectory is roughly planar and follows a curve closely modeled by a parabola. Therefore, at the start of this phase, we were able to give a prediction of the precise location of a touch using a parabolic fit. When we validated our model with a second user study, we were able to make predictions an average of 128 milliseconds before the user touches the screen, with an accuracy of 1.05 centimeters. Finally, when the finger passes below a 1.8 centimeter threshold over the display, we pass along a prediction of the time at which the touch event will occur. Although previous work shows that latencies below 24 milliseconds are imperceptible to humans, we wanted to know if users preferred interfaces with latencies this low. To test this, we conducted a user study with 16 participants. Using the prediction model, we generated pairs of widgets with different levels of latency and asked participants to choose the one that they prefer. Our results show that there is a strong preference for latencies that are only currently achievable through the use of prediction. 12 of the 16 participants preferred effective latencies lower than 40 milliseconds, rather than those of higher latencies.